So today we have the ratio test and then also the nth root test. The ratio test is a very good test, especially if you have something where your a sub n has anything to do with any factorial problems. Well, this particular one's definitely going to diverge, n factorial being something like 5 factorial is 5 times 4 times 3 times 2 times 1. That's a very large item. You can use the ratio test in a lot of different circumstances, but especially when you have factorials. So what you do is you take the ratio of basically the next term and you divide it by the last term, the term before it, and if that ratio is less than 1, if the limit of that ratio, and you notice that we've got the absolute values on here, so if this alternates, it kind of takes care of that alternating part. If it's an alternating series, you generally want to use the alternating series test to begin with. But since it has the absolute value bars on there, this really only tells us that it converges absolutely if that limit's less than 1. Now you notice it's not equal to 1. So if the ratio of the next term to the term before it is smaller than 1, it converges, absolutely. Now, it diverges, period. There's no absolute divergence, just diverges if that ratio is bigger than 1. So what it would mean is the next term is bigger than the last term. Well, if that's true, it's going to definitely diverge. It's going to be bigger than 1, and therefore it diverges or does not exist. The ratio test is inconclusive if it equals 1. Now, that doesn't mean that you can't tell whether it converges or not. You just would have to use a different method. So if you get it to equal 1, that doesn't mean you know it diverges. It just, you don't know anything. So let's see what this looks like in an example. So we take the ratio, or really the limit of the ratio of the next term over the original term. All right, well, the next term would just be 3 to the n plus 1 divided by n plus 1 factorial. So if we were to divide this by the original, well, when you divide by a fraction, it's the same as multiplying by the reciprocal. So n factorial over 3 to the n. And we want to take this limit as n goes to infinity. Now, when we divide these out, you want to treat the 3 to the n plus 1 and the 3 to the n. If you subtract those, if you divide them, subtracting exponents, that would be just 3. The n's basically cancel out. And then n plus 1 factorial is really n plus 1 times n minus 1 times n minus 2, or really just n factorial. So n plus 1 factorial is n plus 1 times n factorial. So n factorials cancel out, and it leaves us 3 over n plus 1. All right, so we still get the absolute values, which really don't do much for us. So we get the limit as n goes to infinity of this particular thing, which equals 0, which implies that it converges. Absolutely. So that's basically it. You take the next term over the original term, and you take your limit. All right, let's look at the next one here. Now, this next one alternates, and the limit would be n over n squared. The limit would go to 0. So I don't need to use this particular thing. I can just use the alternating series test. So it converges by the alternating series test. You never want to use a more difficult test than you need to. So when we look at the limit, you get a power 1 over a power 2 if you were to FOIL that. So that goes to 0, and it alternates. Let's do another ratio test problem just so that we can get a little bit more practice. So anytime you see a factorial, you really want to think ratio test. Now, 5 is one of those where it's a little tricky to think about this. We've got n to the n, that's huge. So like 2 to the 2 would be 2 squared, not such a big number, but 5 5 to the 5th. That's pretty big. And then we're dividing it by, well, if it was 5, it would be 5 times 4 times 3 times 2 times 1. So logically, this doesn't look like it's going to work out so well, because the top, like if n was 5, it would be 5 5s. But then the bottom would be 5, 4, 3, 2, 1. So it wouldn't be quite as large. So this limit does not look like it's going to go to 0. Let's see if the ratio test actually will work for us. So I could already say that this is going to diverge by the nth term test. Which is the one that says if the last term is not 0, it's going to diverge. So that limit is not equal 0. So let's see how it will look like in the ratio test anyway. So we would take the limit of n plus 1 to the n plus 1 over n plus 1 factorial times, so remember we divide by the original, so that means multiply by the reciprocal, and factorial over n to the n. All right, easy part is the n plus 1 factorial and the n factorial. N plus 1 factorial, like we saw in the last problem, that basically cancels out to be just an n plus 1 at the bottom. So we get n plus 1 to the n plus 1 over n plus 1 times n to the n. All right, so let's see here. We got n plus 1, and we have an n plus 1 on top and bottom. So if I cancel out one of these, I can cancel out 1 on the top. So we got n plus 1 to the n over n to the n. All right, so what would that limit be? Remember, we're doing the limit of this the whole time. I'm being a little loose with my limits, and there should be the absolute value bars, although there are no negatives. So the absolute value bars kind of are a little superfluous there. So what is this limit? Well, I've got something plus 1 to the n over something to the n. That plus 1 is not really going to do much in the scheme of when n goes to like 1,000. 1,001 raised to 1,000 over 1,000. This limit really is going to work out to being basically 1, which means that the ratio test actually, doesn't work out so well. So can we even use the ratio test here? No, it diverges by the nth term test, which we know from before. All right, let's set up one more here. So this next one's a little harder to tell. So I got n factorial squared. Okay, so big number squared on the top. And then I've got 3n factorial on the bottom. It's not being squared, but you have to realize that this triples the number inside. It's not n factorial times 3, it's 3n factorial. So that one's a little harder to tell. I can't just tell whether that limit's going to go to 0 or not. It's one of those where I can make an argument either way. I mean, there is a right answer, but just out of inspection, I can't really tell. All right, well, let's see what happens using the ratio test. So on the top, we get n plus 1 factorial, and then all of that is being squared, divided by 3 times n plus 1. All of that squared. Multiply that by 3n factorial divided by n factorial squared. All right. Well, let's see, what can we do to this? Well, bottom here, this is 3n plus 3 factorial, really. I'm missing a factorial here. I've got, I squared it instead of putting the factorial. That's what that's not I. There we go. This is 3n plus 3 factorial, which would be 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial. All right, there we go. The 3n factorial cancels out. So this is what we have on the bottom. All right, so n plus 1 factorial squared, well, what would that be on the top? That would be n plus 1 times n factorial Oh, there we go. And we're going to square that. So now we're going to distribute our squared, and we're going to have squared for each of these parts, and not squared for the whole thing. So the n factorial squared can cancel out. And what am I left with? I'm left with an n plus 1 squared. It's a little hard to see on this one, sorry. So that's all that's left up top, is this n plus 1 squared. And then on the bottom we get this 3n plus 3, 3n plus 2, 3n plus 1, and nothing else. And remember, we're taking the limit of the absolute value of this, which doesn't really do much for us, as n goes to infinity. All right, well, our degree on the top is a squared, and you'd have to FOIL that out. You can't just distribute it in, but in general, it's a squared. On the bottom, if we were to FOIL this out, we would have 1, 2, 3 n's. So squared over cubed, that limit would go to 0. Therefore, it converges by the ratio test. Yay. And that's not one that I would have been able to tell very easily without actually getting into the problem. Some of them you know the answer before you really even try, and others you got to do the whole thing. So the root test really works well if you've got anything that's raised to the m power. And to use it, it converges absolutely if you take the nth root of something and that limit is less than 1. Now, the thing you got to be able to do is take the nth root. So you really wouldn't want to do the root test on something like a factorial, because what the heck is the nth root of a factorial? That's not really all that useful. So you kind of need it to have some sort of power, which happens more often than, I don't know, you would expect in a lot of these problems. Now, it looks a lot like the ratio test in that it converges absolutely. Again, we can put the absolute value bars on these, as long as it's less than 1, not equal to. It diverges if it equals 1 or it does not exist. I think I said equals. If it's greater than 1 or if it doesn't exist. And the ratio test is inconclusive if the limit equals 1. So there's that terrible, we do all that work and it doesn't work. Now, the root test generally is not that much work. The ratio test is a decent amount of work, but the root test, you do it and you kind of see it. So let's see some examples here. To apply the root test, we're just going to really take the nth root of 2n over n plus 1. And all that is raised to the n. Now, the nice thing about it, these n's cancel, and we're taking the limit. And we've got the absolute values of this whole thing, but it doesn't really do much for us because there's no negatives in there to begin with. So that limit equals 2, which means it's going to diverge by the nth term. Oh, not the nth term test, the root test. Now, if you're really good at your limits, you probably could realize and use the nth term test and say, well, that limit of the inside is 2, and 2 to the n, that does not sound like 0 to me. So, yeah, you could use the nth root test, but anything that's raised to an n power is usually pretty good. So, let's look at number 8. E to the negative n. Okay, what in the world does that look like? Well, I could use the negative exponent to make this 1 over e to the n, or 1 over e, all of that to the n. Now, without the nth root test, you can just use geometric tests. So this would be the r for geometric tests. So r equals 1 over e, and in that case, actually a would be 1 because it's the number out front. And not only does it converge because 1 over e is less than 1, but you could also use your formula for your geometric series to tell me what it converged to. Now, using the root test is you would take the limit of the absolute value of, and you're going to take the root. No, I'm putting the absolute value in the wrong spot, sorry here. The absolute value should be on the inside to keep everything positive inside of a root. So the root of the absolute value and should be here as well in the first problem, of 1 over e to the n, which is, like we know, and we're taking the nth root, sorry. Roots cancel out, and you end up with the limit of 1 over e. Oh, I don't need the absolute values at all, which is just 1 over e, which is less than 1, so it converges like we knew. Converges by the root test. So the root test is really, really good for anything that's raised to a power of n. And then you just examine them. So we can take a quick answer for number 9. Well, that's going to diverge because if you get rid of the n, you're going to have n over 500. And as soon as n's bigger than 500, you're bigger than 1. Looking at 10, if the n comes out of here, natural log of n, which is not very large, over n, that is going to go to 0. If you remember, natural log kind of goes like this, and like x would kind of look like so the n would take over. If you weren't sure about the limit, you could always use L'Hopital's rule, because you would end up with infinity over infinity as n got really large. Apply L'Hopital's rule and you got it. So nth root test, anything to the end, that's the key to let us know that we're using that particular one.